Thanks for organizing this workshop, and thanks for the introduction. So yes, I will be talking here about like one of my favorite questions in quantum information is to study from a complexity point of view or from algorithmic point of view how to best encode data. Okay, and the purpose of this talk will be to focus on just encoding a single bit. Okay, and so this is joint work with like two of my PhD students, Idris and Jan. So Jan is around, and Akshay, who was a postdoc in my group and is now started at UBC. Okay, and it's on the archive. Okay, yeah. Okay, so yes, my point of view is Shannon theoretic here. So I will be given a noise model. So I have a perfect description of the noise in my system, and I want to know how to best encode information in this model. Okay, and so more specifically here, so what is my noise model? It will just be a quantum channel. So for simplicity, I'll just assume that we start from a Hilbert space of dimension d, and the output is also a Hilbert space of dimension d. Okay, and so there's two natural questions I can look at here. Is either I want to transmit or store in this noise model. I would like to either send one like a classical message, okay, which I denote by I here in some finite set k, or even more interesting is to transmit quantum information. Okay, but the focus of this talk is, even though the main interest is to transmit or to store quantum information, I think we should understand, or I would like to understand well first the classical case. So how to store classical information in a quantum system. Okay, so the focus of my talk is sending classical information through a quantum channel. Okay, so given such a noise model, my role is to design an encoding and a decoding to optimize the transmission fidelity. Okay, so and here I look at a bit of an idealized setting where I assume the encoder and the decoder are perfectly applied. Okay, so I can optimize over all the set of valid encoders and decoders, and I would like the only source of noise comes from this known channel W. Okay. So let's look at what is known first in the classical case. So, and what I mean by the classical case here is that the channel itself is classical. So it takes classical input and it has some classical output. Okay, so I denoted it by this conditional probability distribution. So X lives in a finite set of size D, and the output is also in a finite set of size D, and I have some probabilities. Okay. And so again, my objective here, so written a bit more mathematically here, is I want to find an encoder, so something that takes as input the message, which I called I, and outputs an X. Okay, so here in this notation, E of Xi is a probability distribution, okay, for every I. Okay, and I want to find an encoder and a decoder that optimizes the success probability. Okay, so what do I mean by success probability here? There are various notions. So here I will focus on the average setting, where I assume that my message I is chosen uniformly at random among all the possible messages. And when do I have a success is when what Bob outputs here, or the decoder outputs, corresponds to what was sent. Okay, so in other words, yeah, my success probability is the maximum over all possible encoders and decoders of this probability of success. Okay, so and as I said at the beginning, my objective is to look at this from a computational point of view. I want to know, given all this data, so the channel W and K, how can I compute this quantity efficiently? Okay, so a result we had about 10 years ago is to understand the complexity of this problem, is to show that, so computing this problem, given the channel, it's in general an NP-hard problem, and an NP-hard problem even to approximate within this factor. But then you have a simple approximation algorithm. Okay, so the simple greedy algorithm you might think of here does achieve this approximation ratio. Okay, and actually this is relatively simple to show if you know about the maximum coverage problem. So the maximum coverage problem is a very standard problem in combinatorial optimization. And it's extremely well studied, and it's well understood that it's the optimal approximation ratio is 1 minus 1 over E. And if you think about it a little bit, you see that the problem of channel coding is very closely related to maximum coverage. Okay, so yes, so you might, so okay, so this is maybe the most studied problem in information theory, and so the most famous statement you might know about this question is Shannon's theorem, and so let me just write it in this language so that we get familiar with the notation and to see that I'm looking at a slightly different angle, things with a slightly different angle. Okay, so I just wrote Shannon's theorem in this language. So here I assume that my channel W is not a completely arbitrary channel that is given as input, but rather it has this IID structure. Okay, so that's why I note it like this. So W is W tensor N. And what I would like to do is, what is the maximum number of messages I can transmit through this channel? Okay. And so, yeah, written with this language, Shannon's theorem says that there is a threshold. So if the number of messages I try to send is less than 2 to this capacity, then the success probability goes to 1. And if I try to send information at a higher rate, so if k is bigger than this capacity, then the success probability goes to 0. Okay, good. So this is the classical setting, relatively well understood. So now let's move on to the quantum setting. Okay. So now my channel W is a quantum channel, so a general quantum channel. So, so there are some results, some easy things that we can derive from the classical results. So because classical channels are just a special case where you assume, for example, that you start by measuring in some fixed basis. Then you get very easily a general NP hardness result with the 1 minus 1 over E. But on the other hand, the algorithms, it's not clear how to generalize them. Okay, because yeah, the main reason is that you can easily interpret. So as I said here, it's related to a maximum coverage problem. So it's a combinatorial problem where you want to find a set with some structure, and so there is a natural greedy algorithm. Here, this interpretation does not exist. Okay, and so in particular, so this is my objective, is to try to see if we can get approximation algorithms. And so even in the very simple case of k is equal to 2, where I simply want to encode a bit, okay, then it's even non-trivial in the quantum setting. Even though, okay, so the k equals 2, from this algorithmic point of view, it's very simple for classical channels, right? Because you have d possible inputs. You just try all the possible pairs, okay, so x1, x2, and for each pair you compute the best probability of distinguishing between the corresponding outputs, and so this gives you a polynomial time algorithm. Okay, so for k equals 2, like determining the optimal encoding is trivial for classical channels. Okay, so what about, but you see now in the quantum case, you don't have a finite number of possibilities, right? So you have, you can choose 2 arbitrary states as input, and you have a continuum of these, and so it's not clear what is the best choice. Okay, so now in the quantum case, let's just rewrite the success probability in this optimal success probability in a way that is similar to Holevo-Hellstrom theorem. So it's very easy to rewrite this optimal success probability as follows, as 1/2 plus 1/2 of something which is called the contraction coefficient. And so this contraction coefficient is this quantity. So it's so I take a channel, and it is well known that the trace distance and any reasonable measure of reasonable distance measure will decrease after I apply channel, right? So the contraction coefficient is by how much does it decrease in the worst case. Okay, so it's by data processing inequality, this is always smaller than 1. And so the contraction coefficient measures by how much it is smaller than 1, okay, in the worst case overall possible states. Okay, so the contraction coefficient, this is a well-studied measure, well-studied for multiple measures, so even in the mathematical physics literature, but recently it has regained interest. So I think here I put a paper related that used this for differential privacy. It's also used in the context of studying noisy circuits. Yes, so okay, so now my objective is to understand the computational complexity of computing this contraction coefficient of a channel. Okay, and so here are the results. So I will show you like three results that we have on the computational complexity of computing this contraction coefficient. So first, the first result is to show the NP hardness to approximate this within some constant factor. And this is even the case if W has a classical output, right? So if W has a classical input, then the problem is trivial. So the input has to be quantum. But here we show that if the input is quantum, but the output is classical, then it is NP hard. Okay, so the second result is, you might wonder here, so maybe one of the regimes, which is the regimes of interest here, is when this contraction coefficient is close to 1, right? So when the contraction coefficient is close to 1, it means that you can transmit a bit perfectly, right? So when it is equal to 1 means that you can transmit a bit perfectly. Okay, so one specific question of interest is, can I find a perfect encoding of a bit? Okay, so a priori this result does not tell us that it is NP hard to decide whether it is possible to encode a bit perfectly or not. Okay, so that's why we have the second theorem here, which is about this complete case, is about to decide whether the contraction coefficient is equal to 1 or not. And in this case, we can also show NP hardness, but here the gap is, it's not a constant factor, but it's like 1 versus 1 minus 1 over poly. Okay, and okay, so these are negative results or hardness results. So to complement this, we give an algorithmic result, which is, so it's a hierarchy of semi-definite programming upper bounds on this quantity. Okay, so these are, yes, go ahead. Yeah.
Sorry, is it clear that this problem is in NP?
Yes, because you can give the two states, right? Okay. Yes, you can give the states. Or you can give the encoding if you want to think of the, yeah, I mean the encoding of 0 and the encoding of 1. Yeah, so. Yes, by the way, here maybe I can say this remark now, is that now I didn't specify exactly how do I encode the problem. So here I'm assuming that the channel is encoded by, let's say, the Choi matrix, and I give the entries, right? So it's explicitly described. So I'll discuss in a bit that people studied like related problems in different models, but I'll say that in a bit. Okay, so I'll try to discuss these 3 points. So I'll try to focus more on this, the second aspect. But okay, let's see, depending on time. So okay, so I'll talk first briefly about the general hardness. Okay, so the general hardness. So the idea here is we do a simple reduction to one of the Grothendieck problems, and so in particular we use this one. So the literal Grothendieck problem, and it's the following: it's given a linear map, it's to compute the 2-to-1 norm, okay, of a linear map. Okay, so this was shown to be NP hard to approximate in this paper within some factor, and so the idea here is to encode this problem in some in the contraction coefficient of some channel. Okay, maybe I just very briefly go through the reduction. It's relatively simple. So yeah, it's simple. It's more convenient to work with the duals here everywhere. So yeah, so I write the 2-to-1 norm in this form in terms of the norm of f star. Okay, so I write it like this, and also, so the idea is, given such an f, right? My reduction is from this problem. So given such an f, I construct some channel. Okay, so I construct the dual of the channel of interest. So it will be this actually very simple channel. Okay, so W star. So remember, W will have a classical output, which corresponds to the fact that W star has a classical input. Okay, so this y, the small y, is a vector. Okay, so it will output this vector f star of y. Okay, and E is some orthogonal, some vector which is orthogonal to all of Rn. Okay, so it's a new vector in my space. And so my output here is just this sort of rank 2 matrix, right? So f star y E transpose plus E fy transpose. Okay, and so why this specific channel? So the idea is just for this specific matrix, it's possible to relate the lambda max or the lambda min of this matrix to the 2 norm of f star y, right? So if you just compute the eigenvalues of this matrix, you'll see that it's directly related to the norm of this, and the norm, the 2 norm of this fy star is directly related to this f2 to 1 norm, okay? So it's a relatively simple construction. You just have to work a little bit more to make sure that this W is actually a channel, but this is basically the idea. Okay. Good. So now let me focus a bit more on the hardness of the complete case, right? So, okay, so again, so this is, I'm given a channel. I want to determine whether the contraction coefficient is 1 or smaller than 1. Okay, so I just rewrote here, this corresponds to deciding if I can transmit a bit perfectly. So another way of saying it is that there's 2 states, rho 1, rho 2, which you can assume are pure. You can also assume they're orthogonal, such that the trace of W rho 1 times W rho 2 is equal to 0. They're orthogonal. Okay, so if you like some graph theory and quantum graph theory, so you can reformulate this in terms of the confusability graph of the channel W. Okay, so the confusability graph of some channel W is, it's a generalization of the confusability graph for classical channels, for those who know it, but now it's defined in terms of, it's not a graph in the conventional sense, but it's a subspace. Okay, so and it's a subspace where you take your Krauss operators, you multiply them, and you take the span. So this gives you a subspace, and this is called the quantum graph. And so with this way of formulating things, like having a contraction coefficient of 1 is equivalent to this quantum confusability graph having an independence number bigger than 2. Okay. And it's equivalent also to having a rank 1 state in the orthogonal of this confusability graph. Okay, so yeah, so now let me make this comment on the encoding. So this problem has been studied, maybe not with this form, but more with this form of independence number for quantum graphs, in these works by Beghi and Shor, and later by Kolf and Mehta. They studied the problem where now the input, instead of being given explicitly as the channel, but rather you give a circuit. So the circuit defines a channel, okay, and you ask for this channel which is implicitly defined, do I have this property or not? Okay, and it was shown that in this setting it's QMA hard. Okay, so let me now get into the reduction. I'm going to check the time. Okay, so it's relatively simple to rewrite this problem as a separability problem. Okay, so again, the set of separable states, I assume everybody knows this. So it's the convex hull of the set of product states. And so here I introduce this LSEP. So yeah, it's usually written as HSEP, but when it's a maximization, so now I wrote it we chose a slightly different notation to because we used minus. It was a bit more convenient for us. So you minimize some linear function on the set of separable states. Okay, so and it's possible to rewrite this condition on the channel as a separability problem. Okay, so you just take the choice. So here J of W star W is just you take this this linear map and you compute the Choi state of it, or the Choi operator. Okay, so you see here it's directly related to a separability problem, and so the separability problem, it was extremely well studied from a computational point of view, and there are several papers. And so it's known in particular that like designing membership, and here more relevant for us is optimizing linear function is NP hard, and Sev in particular showed this. But this, we cannot use it directly because for us it's a bit of a special case. So here, so in particular the linear function that we're looking at has a specific form. Okay, so we have to do a bit more work for that. So maybe I go quickly over it. So we use this, like it's a constraint satisfaction problem. So the exact details of what it is, what this problem is, don't matter so much. So the instance is a graph, and I'll assume it's of size n. So, and the basic idea is to like reuse some of the tools that were introduced in order to show the hardness of separability. Okay, but we have to really reuse their techniques. So in particular, we have such constructions which map these CSP problems into the separability of some projectors. Okay, so these are sometimes also written in terms of proofs for like quantum proofs, two-prover quantum with short proofs for these CSP problems. Okay, but for us, let's just look at it abstractly as just constructing this projector. Okay, this projector, such that its separability properties capture whether our instance is satisfiable or far from satisfiable. Okay, so given this projector, we want to construct a channel, right? So our objective is to construct a channel and to encode this problem into a channel. And so the way we do this is by changing, so taking this projector and constructing some subspace and then modifying it slightly so that it's a quantum graph. By the way, quantum graph is more commonly known as an operator system, for those who are more familiar with this vocabulary. And from an operator system, we know that you can construct a channel which has the corresponding confusability graph. Okay, and so with this construction, I skipped some details, you can get the equivalence between like that the contraction coefficient of the constructed channel is 1 and that the like LSEP of the pi is equal to 0. Okay, and so which is itself equivalent to the satisfiability of my instance. Okay, so this is a rough sketch of the proof. Let me now get quickly to the algorithms. So the problem is hard, right? So there is no hope to get a polynomial time algorithm, but we can do something weaker, which is we can come up with a family of semi-definite programs, which is here. So it's indexed by m, and it's of size exponential in m, such that they're always upper bounds on the contraction coefficient, and we can also bound the convergence speed. Okay, and so this is relatively easy using the results from that we had with Mario a few years ago for the separability problem with linear constraints. Okay, so of course, if you plug in the like m so that this is smaller than epsilon, you will not get the polynomial time algorithm. And one can maybe compare these semi-definite programs to, yeah, there has been recently lots of studies of related to this quantum doubling coefficients. So it's SDP upper bound on the contraction coefficient, which is motivated by, in the classical world, something called doubling coefficients. And so you can think of the SDPs that we have as alternatives to these quantum doubling coefficients, and that you can in particular run. And we see actually that the first level of this hierarchy gives us a better bound than this quantum doubling coefficient. Okay, so here we applied it on like a few copies of the depolarizing channel. Okay. Yeah, good. By the way, an interesting remark that I didn't know before seeing this is that the best success probability for one copy of the depolarizing channel is exactly the same as for 2 copies. Okay, for encoding a bit. You don't gain anything by using a second copy.
Well, if you go to 3 or more?
Yeah, if you go to 3, yes, because this is actually exact, right? So So yeah, so this line is 1 copy or 2 copies, and this line is 3 copies, and this is exact, by the way. Yeah, so we can check that the SDP is actually exact. Good. So let me conclude. So in this talk, I looked at the computational complexity of some problem which has several different, which you can describe in several different ways. So one of them is the contraction coefficient of a quantum channel, or optimal encoding of a bit in a quantum channel, or if you want, deciding if a quantum graph has an independence number, which is at least 2. Okay, so a few open problems for future work. So yeah, we didn't talk about approximation algorithms. I think this would be very interesting. In particular, so one particular way of doing this is, so as I said, so separability was extremely well studied, and so there are in some there are sub-exponential time algorithms, and there are approximation algorithms in some settings with some norms. And it would be interesting to see if these techniques can be applied in this case. I don't know the relation to. There is some relation to separability, but it's not clear either way actually. So if you go from one way to the other, you lose the dimension factor, and if you go from one, you come back also. So it's not clear how to use these. Also, yeah, better algorithm for structured channel, like channels which are IID, for example. And also, as I mentioned at the beginning, so the thing which I'm even more interested in is encoding a qubit, not just encoding a bit, but encoding a qubit. And we have a few results in this direction. This is work in progress. Okay, thank you.
We started a bit later, so there is a couple time for a couple of questions. Yes.
Oh, so you proved your theorem 1 using a channel that outputs a classical state.
Yes.
And you showed that it's NP hard. So if the channel instead outputs a quantum state, do you think that it can be harder than that?
Yes, so we have actually in the paper a slightly, so that if the channel is completely quantum, we have a hardness result with a factor which is a little bit bigger than that, right? So so which we can.
Is it still constant?
Yeah, it's still constant, but it's the constant is slightly harder. Yeah, so, but actually we don't know whether this is tight at all, right? So we don't have any corresponding algorithms. So yeah.
Yes, I can bring this.
Thanks for the nice talk. I was wondering if we can say anything about the hardness of the asymptotic problem. So even if like a single copy of the channel is strictly contractive, many copies can have coefficient equal to 1. And this is related to this super duper activation phenomena. Like your single copy one-shot zero error capacity can be 0, but if you have the asymptotic IID setting, you can activate and transmit a bit optimally, like without error.
So I would say that. So here you're thinking about like taking tensor powers of the channel, right?
Yeah.
So for me, at least, okay,
some
with the perfect case, I don't know, but with the because so if your channel is so either your channel is completely trivial in the sense that the output is independent of the input, in which case it will have a positive capacity, and so if you take arbitrary large copies, the contraction coefficient will go to 1. Right? And sorry, so I said if the channel is non-trivial, then the contraction coefficient will go to 1, and otherwise the contraction coefficient is 0, right? So so if you take this limit of arbitrary tensor powers, like the value of the contraction coefficient is either 0 or 1, or goes to 1. But I think what you're asking is you want to be exactly 1 at some n,
at some finite
right?
n.
So this I don't know. Yeah, if the question is there a finite n such that it's exactly equal to 1? Yeah, I don't know. It might be easy, might be hard. I don't know.
Like, I think people think that it might actually be undecidable to check whether this is the case or not.
Okay, whether there is a finite n, whether it's okay. Sounds good.
Or like in general, like computing this independent series of IID copies of a non-commutative graph.
Yes.
This can like be a pretty wild sequence of integers. And even the limiting value, which is the Shannon capacity of the
Yes.
graph, that's like
Oh yes, even in the classical case, I would
Yeah,
say,
yeah,
yeah,
yeah.
even in the classical case, it's not, yeah,
Thank you.
yeah, thanks.
There is time for one more short question. Yes.
Thanks for the great talk, Omar. So that theorem one looks like a hardness of approximation result.
Yes.
So have you tried to reduce that to the separability problem and try and maintain the hardness of approximation result? Because it's still open this constant distance
Yes,
regime,
yes,
right?
I know.
Yeah?
No, but yeah, as I said, it's, I mean, yeah, I mean, the only way we know how to relate it to separability, so it's either, yeah, so here, in the complete case, yes, fine, but here to show the soundness, you lose a dimension factor, either way. So if you want to go from this way to, so yeah.
Thanks a lot for this great talk. And I ask the next speaker to come.